Hello everyone. Today I'm going to talk about the paper Erasure Well Pipeline Repair Scheme for Erasure-coded distributed storage systems. My name is Tong Liu and I'm from Temple University at Philadelphia. So first, let's look at the introduction and background of this paper. Erasure coding is a popular fault-tolerant scheme which provides data reliability by adding data redundancy. Among multiple Erasure code families, the Reed-Solomon code is the most widely used code in practice. An RS code is usually configured with two parameters n and k, where n represents the original data chunks and k is the parity chunks. So the figure below shows the encoding process of an RS-53 code. We can see that five original data blocks will be encoded with a encoding matrix, and a coded stripe will be generated, which include the original five data blocks and the three parity blocks. And any equal or less to three blocks are filled within this coded stripe, we can always reconstruct by decoding. Nowadays, modern large-scale data centers hold data in thousands of commodity storage nodes or servers organized across multiple racks and apply erasure coding to provide reliability. As shown in figure below, each rack has a top-of-rack switch that connects the nodes within the same rack. Outside the rack, there is an aggregation switch which connects all the TOR switches so that the nodes across different racks can communicate. However, this one node per rack placement brings several issues. First, reconstruction requires heavy data download and consumes a large amount of data transfer. Second, the low cross-rack bandwidth becomes the bottleneck of the whole repair process. In addition, all the data up nodes happen in the recovery node or rack, which makes the system node imbalanced. As discussed, the high cross-rack network traffic and the node imbalance is caused by the fact that the recovery node can only start the decoding process after it receives all the information from the other nodes or racks. To mitigate the high traffic and balanced node, it would be intuitively better if the data transfer and decoding process could be distributed to other nodes or racks. So partial decoding can be considered here. For user coding, in the matrix encoding and decoding process, all the operations are calculated according to Galois field arithmetic. In the Galois field, the results of any operation still lie in the field. Another important property of GF arithmetic is that addition is equivalent to XOR. So consider an RS42 code with four data chunks from D0 to D3 and two parity chunks P0, P1. When D2 fails, we assume D0, D1, D3, and P0 are selected to recover the data. Then the recovery equation of D2 would be D0 XOR D1 XOR D3 XOR P0 equals to D2. With partial decoding deployed, the default recovery can be divided into two parts. D0 XOR D1 will generate an intermediate block I0, and D3 XOR P0 will generate another intermediate block I1. In the second step, I0 will XOR I1 and generate the recovered data block D2. With partial decoding, the lost data can be decoded partially and in parallel, thus mitigating the transfer bottleneck and load imbalance issues. Based on this, we propose the first design of RPR scheme, the inner rack partial decoding. The algorithm inner runs for each rack when the repair process starts and takes the nodes involved in the repair as the input. Inner divides the nodes into several pairs and performs partial decoding recursively until the final intermediate block I is generated. The figure shows an example of using traditional repair and inner partial decoding repair. So the first subfigure shows the traditional repair process with an RS42 code when single block failure occurs. We can see that it will take four time steps, and in each time step, a cross-rack transfer will happen, which will transfer one data node or parity node from the original rack to the repair rack. So the subfigure below shows the repair process with the inner rack partial decoding deployed. We can see that the difference here is that in the first time step, there will be an inner rack transfer within the racks R1 and R2, where the intermediate blocks will be generated. And then in the second time step, the intermediate block from R1 will be transferred to R2 and then generate the final recover data block D1 here. And then in the last time step, the D1 will be cross-rack transferred to the repair node or repair rack. So as we introduced before, the inner rack bandwidth is around 10 times the cross-rack bandwidth. So the cross-rack transfer time step is around 10 times of the inner rack transfer time steps. So with partial decoding deployed, now the total repair time or the total transfer time is only a half of the traditional repair. So for simple RS code, after each intermediate block is generated, the cross-rack transfer schedule would be straightforward. However, when multiple failures occur or when there are more nodes involved in the repair process, the inner rack and the cross-rack transfer schedules would be much more complex. So below shows an example with RS62 code, and it has two schedules. The first schedule, we can see that in the first time step, there will be three inner rack transfers within racks R1, R2, and R3. And after the intermediate blocks are generated within these three racks, there will be three following cross-rack transfers to transfer this intermediate block to the repair node or repair rack, and finally repair the reconstructed block there. In schedule 2, the first time step is still the same, which is the inner rack transfer for R1, R2, and R3. The difference here is that in time step 2, R1 will transfer its intermediate block to R2, and simultaneously R3 will transfer its intermediate block to the repair rack. So this step is done in parallel. And then in time step 3, R2 will transfer its intermediate block to the repair node and generate the final reconstructed data block. So we can see that compared to schedule 1, schedule 2 used the parallelism and saved repair time for one cross-rack transfer time step. So we can see that the different cross-rack data transfer schedules will have very different total repair time. So how can we arrange the schedules so that always achieve a lowest transfer time? To address this issue, we propose a pipeline-based greedy algorithm cross, which aims to maintain the data consistency during the entire process, as well as achieve the optimal total repair time. The details of the proof can be found in the paper. The cross algorithm works together with the inner algorithm. Whenever inner finishes the inner rack data transfer and produces the intermediate data, cross will give the optimal cross-rack transfer schedule based on the current node and the rack transfer status. So let's look at the process of the cross algorithm. First, for each rack, if an inner rack partial decoding can be conducted, then we start the inner rack transfer and the partial decoding. Since inner rack transfers are faster than cross-rack transfers and can reduce the cross-rack transfer data volume, they should always have priority over cross-rack transfers. If an inner rack transfer cannot be scheduled, then start a cross-rack transfer with any other rack which currently has no inner rack transfer. Either its inner rack transfer would have finished, or it does not need to conduct one. The recovery rack can also be selected, but only when every non-recovery rack is busy. Third, when the inner rack transfer finishes, start a cross transfer with any other rack that does not currently have a cross rack transfer. Fourth, if every other rack has a cross rack transfer, then wait until the one finishes first and then start the transfer. Finally, we repeat recursively until all the racks finish their cross-rack transfers or the recovery node receives all the intermediate data. Previous work has found that single block failures are the most common and the dominant failures in distributed storage systems. To optimize for this case, we proposed a pre-placement scheme which utilizes the previously mentioned property of the RS code. So intuitively, to reduce the cross-rack data transfer, it would be better to transfer as much information as possible in each cross-rack transfer. Thus, to reduce the amount of cross-rack transfers and avoid building the decoding matrix, the best way is to put P0 with the data block instead of parity block in the same rack. For an IS code, if the first parity block P0 is placed with all data blocks in the same racks, then assuming the block failure rate is the same for all blocks, there is a 1 over n chance that there is no need to build the decoding matrix when a single block failure occurs. That is because in the Van der Monde matrix, all the values in the first row of the coding matrix are 1. Our experiments show that building the decoding matrix takes around 80% of the total decoding time. When one failure occurs, the failed block can be reconstructed by using the decoding equations as we mentioned before. However, when multiple failures occur, the repair procedure becomes more complicated since more decoding equations are required. Existing cross-rack repair schemes, such as CAR, can only tolerate single failure scenario. Similar to inner and cross, we propose inner multi and cross multi algorithms which can reduce the cross-rack traffic and the total repair time when multiple failures occur. Assume there is an NK erasure coded system with original data blocks D0 to Dn-1 and parity blocks P0 to Pk-1. Then the encoded functions for this system are shown in equation 7, where Eij is the encoding coefficient. Further, assume that there are k failed blocks df to dfk-1, which belongs to d0 to dn-1. Then from equation 7, we have equation 8, where e prime ij is the coefficient after the conversion. Note that the blocks on the left side of each sub-equation in equation 8 do not include the failed block on the right side of each sub-equation. So to recover each failed block, the data on the left side of each equation is needed. Once again, we can use partial decoding and cross-rack scheduling to reduce the total repair time. Assume that the stripe is distributed across Q racks, then for each sub-equation in equation 8, every rack can only transfer an intermediate data block Ij to the recovery node or rack, which is the partial decoding result of the available blocks in the current rack. Then equation 8 can be further written as equation 9 here. In the multi-block failure scenario, the partial decoding in each rack needs to be conducted multiple times to obtain all the required intermediate data blocks. After the intermediate data blocks are generated, each sub-equation in 9 can be considered as a single block failure scenario as previously analyzed. The difference is that there will be multiple cross-rack transfers for each rack. Then the inner multi and cross multi algorithms corresponding to the multi-block failure scenario can be summarized as in algorithms inner multi and cross multi. Due to the time limitation, I'll skip the details of these two algorithms here, but it can be found in the paper. So we evaluate the RPR scheme from two aspects, the simulations on the CMIX simulator and the evaluation on Amazon Web Service EC2. So first, let's look at the CMIX simulation. CMIX is a platform for full system simulation that is sufficiently generic to model embedded systems, desktops, clusters, and more. And in our experiments, when the shaper is applied to achieve the different inner rack transfer and cross-rack transfer bandwidth. The Erasure coded RPR prototype is built based on the Erasure library v2.0, and each data or parity block is 256 megabytes. For Amazon Web Services 2 evaluation, most settings are same as CMIX simulation. One thing to note here is that to simulate the rack level data transfer, we launch instances in 5 different continents as shown in the table below. Next, let's look at the experimental results. We first focus on the single block failure scenario, in which a random data block in the encoded stripe is assumed to have failed. In this part, we compare the repair performance in two aspects, the cross-rack traffic and the total repair time. The comparisons are conducted among RPR, traditional repair, and CAR, which, to our knowledge, is the state-of-the-art cross-rack single-failure repel scheme. The left subfigure shows that both RPR and CAR can reduce the cross-rack traffic compared to the traditional repel scheme. The right subfigure shows that the total repel time difference among the three repel schemes. In the CMYX simulation, based on the 6 common RS code configurations, RPR can reduce the total repel time by an average of 67% and up to 81.5% compared to the traditional repel. Compared to CAR, RPR can reduce the total repel time by an average of 24% and up to 37%. For EC2 evaluation in single block failure scenario, we use the same code configuration as in the CMYX simulation to compare the total repel times of the traditional repel, CAR, and RPR. The cross-rack traffic is the same as the CMYX simulation. The right subfigure shows the total repel time results, which indicate that the repel time difference of CAR and RPR is more significant than the CMYX simulation results. This is because in EC2 machines, the decoding time with the traditional decoding functions of a 256 megabyte file is around 20 seconds, while our optimized decoding function only costs around 2.5 seconds. In the EC2 experiments, RPR can reduce the total repel time by an average of 67.6% and up to 80.8% compared to the traditional repel. Compared to CAR, RPR can reduce the total repel time by an average of 37.2% and up to 50.3%. As discussed before, RPR also supports the multi-block failure scenario for any RSNK code, while CAR only focuses on the single failure scenario. With respect to the cross-rack transfer traffic, RPR uses an average of 29.35% and up to 50% fewer cross-rack data transfer compared to the traditional repel scheme, as shown in left subfigure. The results in right subfigure shows that the RPR reduces the total repel time by an average of 40.75% and up to 64.5% compared to the traditional repel scheme. For multi-block failure scenario, when evaluating the total repel time, we divide the scenarios into two categories: worst case happens and non-worst case happens. More details can be found in the paper. For multi-failure scenarios of EC2, the cross-rack transfer traffic is the same as the CMYX simulation, as shown in the left subfigure. The right subfigure shows that the results when the worst case does not occur, RPR can reduce the total repel time by an average of 39.93% and up to 61.9% compared to the traditional repel method. So in conclusion, we propose RPR, a record-well pipeline repel scheme comprised of three techniques: inner-rack partial decoding, cross-rack pipeline scheduling, and data parity placement. RPR supports both single-block and multi-block failures. And we conduct experiments on both CMYX and AWS EC2. Results from both platforms show that in single block failure scenario, RPR significantly improves the repel performance compared to the traditional RS code as well as CAR, with total repel time reduction of up to 81.5% and 52% respectively. And when multiple blocks fail, RPR also improves the repel performance compared to the traditional RS code repel, with total repel time reduction of up to 64.5% and cross-rack data transfer reduction of up to 50%. Thank you. That's all for this presentation.